topic of this is about relations and functions. So a relation is a set of ordered pairs. So here I have a relation that all the information is -3, 3, 2, 2, -2, -2, 0, 4, 1, -2. So what I'm going to do is I'm going to graph a little grid right here. 2, 3, 1, 2, 3, 1, 2, -2, -2, 0, 4, and 1, -2. Okay. This is an example of a discrete graph because it's just the points without any connecting lines or segments. It's also possible to model it with a mapping. Now, a mapping has, sometimes you see them as rectangles, sometimes you see ovals. You have your inputs or your x-coordinates on one. Notice I just put them in order from least to greatest. 2. And then you just draw arrows connecting different ones. So -3 is going to go to 3. -2 goes to -2. 0 goes to 4. 1 goes to -2. And 2 goes to 2. Okay. Mappings are only useful for smaller amounts of things. So another example of a mapping would be like New York goes to Mets, and it goes to Yankees. Boston goes to Red Sox. Okay. So a function is a special relation that has for each input only one output. So here, is each input only going to one output? That's a yes. How about this one with my New York and Boston? That's a no, because you can see how New York is going to two different things. Okay. So, determine if the following are functions. I'm going to say. So, take a minute and determine if these are functions. So, I have 2 discrete graphs and 4 continuous graphs. Alright, so this one is no, because you can see how the input of 1 is going to an output of 0 and a positive 1. This one's yes. This one's yes. Yes. No. No. And you can see right here how the input of 2 goes to 2 different things. Okay. Same kind of thing here, that you have the input of 0 is going to 2 different values. And so these are all examples of that they're not passing the vertical line test. So, domain is the set of inputs or x values, and range is the set of the outputs or y values. So when I take a look at, I'm actually going to go back up here and do a couple of domains even on these. So let's find the domain here. Your domain is -2, 0, 2, and 3. So -2, 0, 2, and 3. So on here, because I have a discrete graph with just a selection of points, I am doing some curly brackets, which I refer to as Mr. Incredible profile, because they have a really big forehead, tiny nose, big chin. Okay. And I'm listing the values from least to greatest. So then here I talk about like -2 for my range, -1, 1, and 3. Notice that these are not matching up. Okay, so it's not a list of my coordinate points. Okay, here's another one that worked. So my domain, as I take a look at this, see how the arrows are continuing forever? Okay, so it's going to keep on going towards negative infinity this way and towards positive infinity this way. So my domain is negative infinity to positive infinity. See why we looked at interval notation in the previous video? It's so that we could use that skill here. My range, the lowest we go is 0, the highest we go is 1. Or actually it's -1 to 1. I apologize. -1 to 1. And we're going to put brackets on that. So, and I'm going to actually do the domain and range on this one as well. So you don't have to be a function to have a domain and a range. Our domain here is from 0 to 2. Closed brackets on both. And my range is -2 to 2. For that half circle or semicircle, that is not a function. Okay, so find the domain and range in interval notation. So my domain here is from -2 to 4. It's including the -2, but it is not including 4. And my range is from 1 to 3, including the 3, not including. All right. So if I'm looking at a graph, we can use the vertical line test to tell, oh, well, I wrote test there twice, to tell if the graph is a function or not. So if it passes a vertical line test, then if a vertical line can be drawn at every point and it only intersects the function once, then it is a function. If you can draw a line in a relation and it crosses the relation more than one time, it's not a function. So this is a function. Since we're going now notice this particular graph doesn't have arrows, but notice how it goes all the way to the edge and it's not stopping and it's not giving me some sort of large indication that it's stopping. So we'll say its domain is all real numbers. So again, that negative infinity to infinity. We also simplify this. All real numbers, so fancy R for all real numbers or rated. And before it was a hashtag, it was a number symbol, so I'm sticking with it. Our range is the same. I'm going to go with the fancy R that time. This one is not a function. And our domain is -2 to 2. And -2. And try the third one on your own. Okay. All right. Function notation. It's when we write f of x, okay? And it's the same as y equals f of x. It's a more sophisticated way of writing, and as we head into our mathematical career, we want to utilize more sophisticated methods. So if I wanted f of 3, I'm just going to take the x and make it -3. We got -9 plus 2, -7. What's nice about when you write something in function notation, you have both the input and the output instead of just having y equals -7. So here, f of 5, 17 plus 2, 7. So f of 5 is 17, which is the same as saying the chord at point 5, 17 would be on the graph if I was graphing it. Now I have a few spicier ones here. Instead of having f of a number, I have f of x plus 3. When I go to find f of x plus 3, where my x was, so see how there was an x right there? And that matches that. Here I'm going to have x plus 3. So I'm going to still have 3. It's plus 2. But this inside piece right here where I'm placing it, I'm going to have x plus 3. X plus 3x plus 9. So all I did there was just distribute. And then I'm going to combine my terms. So if I input, instead of inputting a number, if I input the expression x plus 3, the output is 3x plus 1. If I input negative x, I'm going to have 3 times negative x plus 2, negative 3x plus 2. if I input the quantity x plus h. 3 plus h. 3x plus 3h. And last but not least, find x when the output is 11. So I'm going to make my output 11, and I'll 3x plus 2. Let me solve for x. So take a minute and try the one on the next page. And that concludes this video.